Yeah, so last time we talked about, some basics of decoupling, like what is decoupling. We talked about what did Bourgain and Demeter prove for decoupling for the paraboloid, or we talked specifically about the parabola. And we talked about, is their estimate sharp? We briefly talked about how to compute Fourier transforms of indicator functions heuristically. Right? Today, and so what we did was we reduced to saying, well, there's one critical decoupling estimate that we prove, and once we prove that estimate, we sort of interpolate between the trivial L2 decoupling and the trivial L infinity decoupling to get the sharp result. And in the notes previously, I mentioned it's sketched. Of course, if you do want notes, I have these notes in this PDF. They're just handwritten. Feel free to email me. Okay, so let's recall. So the goal for today was hopefully to actually give at least one proof of decoupling for the parabola. Yeah, hopefully we'll accomplish it. But if not, we'll just continue on the next time. Okay, so today we're going to prove goal L2, L6 decoupling for the parabola. Okay, so let's recall some notation. So recall. So I will, just for this particular set, on this particular board, I is in P delta. What does this mean? I is an interval of length delta, and P delta is a partition of 0, 1 into intervals of size delta. So partition 0, 1 into intervals of length delta. Strictly speaking, then, when I write this, okay, yeah, delta needs to be 1 over an integer. Let's not worry about any of these integer conditions. They can all be fixed. Theta I, remember, is our note. So given an I in P delta, theta I will be the set S plus S, will be a delta squared neighborhood of the piece of parabola above I. Okay, this is delta squared neighborhood of parabola above I. Strictly speaking, as I've defined on this board, I needs to be interval size delta. Of course, this definition theta I can be just for any interval. Okay, let's draw the picture. Pictures are always key. If you try to do decoupling without drawing pictures, you can do it, but the pictures usually motivate everything. Okay. So this is delta squared, and because we're always going to be working in the interval 0, 1, this delta squared neighborhood of the piece of parabola above I is basically a delta by delta squared rectangle pointing in some direction. Okay, so this is also basically length delta. Okay, what is decoupling? Okay, so we're going to let dp of delta be the best constant such that the L6 norm, or not, let's define dp of delta first, and then we'll concentrate on 6. Less than dp of delta, let's say I such that this estimate is true for all f Fourier supported in the union over this. Okay, so let's briefly explain what I just wrote. So dp of delta is the best constant that I can put such that this is true for all f with Fourier transform supported inside the delta squared neighborhood of the piece of parabola above 0, 1. Okay. For all f Fourier supported in this guy, this set over here is literally just the delta squared neighborhood of the piece of parabola above 0, 1. And remember, saying that something is Fourier supported in this region means for all f whose Fourier transform lives here. And also remember that what is decoupling? Well, if f is Fourier supported in this neighborhood, then what is this saying? Well, this is really saying that, well, what's the LP norm of f? Well, the LP norm of f is, of course, the LP norm of the sum of the f theta i's. Okay, this is just by definition the fact that f is Fourier supported in here. To see this, you just take Fourier transforms on both sides. And so what is dp delta saying? dp delta is saying, well, how much does it cost to force square root cancellation to happen inside this sum with respect to what? With respect to the LP norm and the little l2. Okay? So of course you have a trivial bound that follows from Cauchy-Schwarz, and of course Bourgain and Demeter's result. So let's recall last time BD 14 in the case of parabola, in the parabola case. Was that dp of delta is bounded by a constant depending on epsilon times delta to the minus epsilon plus 1 plus delta 1/2 minus 3 over p. Okay, and last time we showed that the lower bound for dp of delta is just this term, so their estimate is sharp. And furthermore, by interpolation, you know, when do critical things happen? Well, critical things happen when these two terms are equal, and this term happens when p equals 6. And so to prove this, it suffices to show the p equals 6 case. The key word is interpolation. In other words, d6 of delta is bounded by delta to the minus epsilon. And remember, this notation means that there exists a constant depending only on epsilon such that dp of delta is less than or equal to c epsilon times delta to the minus epsilon times this. Right? Okay. Great. Are there any questions? Okay. And last time we also compared this estimate with the sort of reverse square function estimate, and we talked about what makes decoupling estimates great. And it's because sort of this problem says, well, it sort of shrinks the problem. It makes the problem easier. Instead of, I want to know the LP norm of f. Well, what does this decoupling estimate do? Well, it says, let's say I knew how to break it down into, not, this is the target scale. Let's say I could make it down into an intermediate scale. I'll call nu. Okay, then what it says is, well, up to paying decoupling at length scale nu, I break up the LP norm of f into LP norm of, you know, at a smaller scale, at an intermediate scale. So I've made the problem easier. This is what makes the decoupling estimates much easier, or much is relative. It makes it easier to prove than the reverse square function estimates, which don't have such iterative property. So today we're gonna make this more clear. And the key lemma that drives a lot of the arguments is, in the case of the paraboloid, it's called the parabolic rescaling lemma. Some people will just call it the rescaling lemma. Some people will just call it affine rescaling. Some people will call this parabolic rescaling even if it's for the moment curve. Anyways, there's rescaling. Okay, so one of the key tools, so now we're gonna hopefully try to finish today the proof of this. Okay, and then once we do so, we've at least can prove one decoupling theorem. So the key tool that drives all of the decoupling theorems, and I really mean all of the decoupling theorems that are proven, there is some sort of rescaling lemma that preserves the decoupling property. Okay, there's always some sort of rescaling, and a lot of the issues with sort of decoupling other surfaces or curves that we don't know nowadays deal with the fact that there's actually no analog of like not having rescaling. This rescaling lemma that I'm going to write is actually a serious obstacle. So parabolic rescaling. Okay, so I know I wrote I here and I meant an interval size delta, but let's briefly digress and move to another definition of I briefly. So let I be an interval of length sigma. Okay, this is, sigma is, you know, of course I lives in 0, 1. Okay, it could be the whole interval, but we should think of it as sort of larger than delta, but smaller than the whole interval. Okay, it's an interval bigger than delta, and let f hat be supported in theta I hat. Oops, theta I. No hat. Okay, so it lives in the sigma squared interval of the sigma squared neighborhood of the piece of parabola that lives above I. Okay. Then the LP norm, I guess I should say the delta squared. So what do I mean by this? Yeah, so this is just S squared plus T less than I, T less than delta squared. Okay. Okay. So what's the LP norm of this guy? All right. What's the LP norm of this intermediate scale? Well, I can decouple it. It's dp of delta over sigma times by the sum over a partition of j into intervals of size delta, of I intervals of size delta, f theta j, LP squared over half. So what does this say? So what does this say? This says, suppose I know the following. Suppose I know how much it costs to break up 0, 1, this guy, into delta by delta squared boxes. Okay? Then, let's consider the easier problem. This is my interval I. Okay? It's an intermediate interval. Okay? Of course, I can still partition this into interval size delta by delta squared boxes. Right? I just literally take the subset. Okay? And then I is of length sigma. Okay? If I know how much it costs to break up 0, 1 into intervals of size delta, how much does it cost to break up I into intervals of size delta? Right? And the cost is, well, it's just dp of delta over sigma. Right? And just as a sanity check, if sigma is 1, in other words, I is the whole interval, of course, you just recover the definition. Okay? So what do you think you should do? Well, the basic strategy is that, well, what do you want to do? You know the whole problem. You know the answer for the whole problem. Now you want a subproblem. So what do? You want to just stretch the interval, right? And then you have to go through the painful calculation, which we will do. Well, I mean, we might give up halfway, but I just want you basically do this once in your life, and then forevermore, when you write papers, you're like, okay, by a change of variables, or you set it up. But I think it's useful to, like, especially starting out, just to remind yourself of how to do this computation. Okay? And in all decoupling proofs, there is some sort of similar sort of rescaling lemma that says this property. If I know how to decouple the whole thing, I call that d of delta. I actually know how to decouple on sort of any intermediate scale. Like, yeah. Okay. So let's do the change of variables. And this is about as messy as we'll get. Okay. So we know that we just need to change variables. Okay. So if you don't want to take notes, you can just, the strategy, and there's just to change variables. So you can watch. Okay. So what do we have? We have. Okay. So the first thing I'm going to do is I'm going to say I is a to a plus sigma. Okay. Yes.
So what do you want to prove? What is your goal?
I want to prove that the LP norm of f theta I is controlled by this expression, right? So so the moral of the change of variables that I'm going to do is I'm going to show you where does this delta over sigma come from. That's the goal of what I'm going to show you. Okay, I'll give you enough details, but I won't give all of them. I'll just get to the point where you can see this delta over sigma. And then I'm going to say you apply decoupling at scale delta over sigma to get this result. Okay. So what does this say? It says that, if I have an intermediate scale, how much does it cost to do this? Well, it costs dp of delta over sigma to decouple. So that's the goal, right? And you can sanity check and pretend sigma is equal to 1, and you get this definition. So the idea will be to change variables, to stretch this, and you also need to dilate it a little bit, and you're going to see a delta over sigma You apply this definition at delta over sigma, and then reverse the change of variables, and then you get this right-hand side. Okay.
So which means that you are showing the decoupling constant is like satisfy the forming option variable, something like this.
The what?
And then you are trying to show the decoupling constant is sort of satisfy the change of variable formula.
Yeah. I mean, this obeys the change of variables formula very, very nicely. As another, there's a corollary of this, and I guess I'll leave it as the exercise. It's that d of delta 1 times delta 2 is less than or equal to d of delta 1 times d of delta 2. Yeah. This does have a point in that you do get almost multiplicativity of the decoupling constants. Yeah. It's a nice little exercise to see that it just follows from this guy. Okay. Great. So let's do the change of variables and to the point where we see delta over sigma. Okay, so what's f theta I of x? Okay, so what is this? I'm for A supported in a delta squared neighborhood of the piece of parabola that lives above I. This guy. So what is this? Literally, it's delta squared A to A plus sigma f hat s squared plus t e of sx1 plus s squared x2 e of tx2 ds dt. Okay, remember e here, e of z is e to the 2 pi I z. Okay. Now, what did we just do? Well, I basically already said the strategy. We need to shift this to the origin and then stretch. Correspondingly, if you don't do this change of variables, you'll realize later it's very useful. We also need to change variables in t to accommodate the fact that we actually want a delta over sigma. If you don't do this, you'll see later in the proof that it is useful to do. So with the benefit of foresight, I'll just write it down this way. Okay, you do what you think you should do with this guy, and you do what you should do with this guy. Okay, great. So then, to spare you the details, okay, apply these change of variables. We can all do this. And rearrange. What are you going to get? You're going to get, let's write a little bit more. Negative delta over sigma squared, delta over sigma squared, 0, 1. Okay, you get what you should get, right? There's nothing interesting that happened so far. The only interesting that happened so far was that, well, you start seeing a sort of delta over sigma neighborhood, delta over sigma squared neighborhood show up, right? But that's assuming that if you could write this as some function g hat of, s comma s squared plus t, right? So how do we organize this? Okay, so let's rearrange a little bit. If you rearrange the exponential sums, okay, and the ax1 term gets killed off by the absolute value, right? And of course, the a squared x2 term also gets killed off by the absolute value because I'm not integrating over it. And then I'm going to group the linear terms together, the linear x1 and the linear s prime terms together, and then I'm going to group the quadratic s prime squared terms together. So let me write down what just happened. Okay. So every decoupling proof, you have to do this once. And then once you do this once, you're good. So let's keep this term now for now. And then I group the s prime terms together. I get sigma s prime x1 plus 2ax2. Sigma squared s prime squared x2, e of sigma squared t prime x2, ds prime dt prime. And as a side note, you do already start seeing this little change of variables that we talked about last time where we had a little shear matrix. right? You know, this is the matrix 1, 2A, 1, right? And that corresponded to, that takes a vertical rectangle and points it in a certain direction. So you can already see that we've done a similar calculation before, which is true. It's a little side comment. Okay, now, what do you do? So basically the structure of this proof is, you know, if you ever read any other decoupling papers, the structure of the proof is literally exactly the same. Okay, because you've conveniently chosen c squared t prime here, actually as an exercise, you can write this as g hat of s prime comma s prime squared plus t prime for some g. That depends on sigma and a. Okay, and you can write it out. Okay, and it's purely because you've made this extra change of variables here. Okay, so that's a little exercise, but I hope you can believe it. Now you see, once we write it this way, then what we've done? This is basically g Fourier restricted to this neighborhood of the piece of parabola above 0, 1, evaluated at this point, comma this point. Okay, times sigma and sigma squared. So let me write this. So, okay, so what did we just do? Absolute f theta I of x is equal to this mess. Okay, this is just calculus. So far we've done nothing. Okay, so the LP norm of f theta I. Okay, well what is this? And I'm being pedantic here. Just for some brief notation, I'm going to denote that this is the delta squared neighborhood. Okay, do I have yellow chalk here? Yellow chalk. Delta squared neighborhood of SS squared. Okay, I need that little bit of notation for this time. And then what we just showed, that this was then equal to sigma, is there a minus 3 there? 3 minus 3, yeah, okay, there should be a positive 3 times the integral of g theta 0, 1, but the delta over sigma squared neighborhood of it, of sigma times x1 plus 2a x2, comma sigma squared x2 to the p to the 1 over p. Okay, are there any questions at this point, other than I've just done a bunch of change of variables? All right, so what have I done? I've literally just taken this guy, stretched it to 0, 1, thickened a little bit. I've dilated the thing, okay? And when you do that, you do all your calculus, and you get that the LP norm of f theta I is the LP norm of this mess times by this Jacobian term, okay? But the most important thing is that you now can see a function whose Fourier transform is supported in the delta over sigma squared neighborhood of the piece of parabola above 0, 1. That's the most important thing. Okay? So what do you do next? Well, so, well, what do you do next? Well, the next thing you do is you do a change of variables to get rid of these terms. Okay? So if you do a change of variables, you call this y1, call this y2. You're going to Jacobi of sigma to the minus 3. So you're going to get this is sigma 3 minus 3 over p times the LP norm of g theta 0, 1 delta over sigma squared LP. Okay? And then what do? Well, you apply decoupling at scale delta over sigma squared, or delta over sigma. because this is for delta, this is a delta squared neighborhood. Okay, but now this function over here is very supported in a delta over sigma squared neighborhood. So now what's the next step? Apply definition of dp of delta over sigma. You apply it, you're going to get that right-hand side, and then you reverse the change of variables. You reverse all these change of variables, and you're going to realize you get this guy. It's literally the same change of variables. Okay? Are there any questions? All right. So basically the strategy is you just stretch the interval to be 0, 1. Okay. Yeah. It's just tedious. I don't doubt it's tedious, and it's just every time you have so every surface that you've decoupled that has a decoupling has a sort of analogous lemma to parabolic rescaling. Yeah.
You said that sometimes this breaks down and that's a huge problem.
Yeah. So for example,
point to where this breaks down.
I mean, it's just that like this algebra stuff just starts to mess up, right? Like, I mean, imagine for a moment that you had a cube here, right? What are you going to do with the s prime cube term, right? So, for example, you can do some things like one sort of typical example that's not very good is that like if you have the curve ss cubed, s is in 0, 1. If you include the origin, or some neighborhood of the origin, decoupling for this is not, and you want to have some sort of, see, decoupling you have to talk about a region, a partition, not just a curve, right? It depends on how you partition this. If you have the curve ss cubed, and you partition this into intervals of size delta, then you start seeing the curvature, right? Decoupling for these things doesn't have a very nice rescaling, and of course, if you delete the origin, if you let's say start from 1/2 to 1, okay, then this curve is a curve that if I don't start at 0, I start at 1/2. Okay, this curve is a curve that has second derivative bounded away from the origin. Okay, but that's basically just like the parabola. And what happens there is that if you do this lemma, what happens is that maybe you're using a decoupling constant. You redefine your decoupling constant so it's uniform over all functions whose second derivative is bounded away, tilde 1, and it becomes slightly more complicated. Okay, this lemma really does use the very nice algebraic properties of the parabola. Yeah, and even if you're working with curves that aren't necessarily a parabola, there are ways around it, but sometimes it's just breaks down completely, or there might be significant restrictions. Like you can work with the origin, but maybe your decoupling theorem is somewhat weakened or something like that. There are tricks around this, but this lemma really is using properties of the parabola. Of course, if you want to work with the circle, then you could still do it, but here you redefine your decoupling constant with a soup over all the C2 functions in 0, 1 who have derivative between 1,000,000 and 1,000,000th or something. Yeah, you can fix these things, but that becomes too hairy for an introductory course. So we just concentrate on the easy big picture ideas. Yeah. Are there any other questions? Yes.
So I just wonder how useful that's called since
This?
Simple algebra tells us dp of delta squared is equal to square root of dp delta. So for example, we want to know the dp delta as delta tends to 0. Then we just iterate this, and it will give us some.
Yeah, but you have to, when you iterate, you have to start from somewhere. Right, so where do you start? Right, so you still have to prove a decoupling theorem. And so, yeah, your comment reminds me of, so Larry when he would give talks, he always give a sort of fake proof of decoupling that's based on this. And the issue is that, yeah, I mean, you can use this to iterate downwards, but every iteration needs a starting point. And to win, you have to prove at your starting point that you know that dp is small. And you don't know how to do that unless you already know the decoupling theorem ahead of time. So it's somewhat circular. Yeah. I mean, this is, in practice, this is not used so much, this identity. As another exercise, another thing is also known. dp of delta, let's say a large scale, is less than dp of delta times a small scale. And by delta large, I just mean for delta small less than delta large. I have to write it this way, otherwise I'll forget which way it goes. But it just says that the smaller the scale, the harder it is to decouple. And that's also another exercise in change of variables. And I might be lying with these less than or equal. They might be less than tildes. Okay. Yeah. But there are some functional properties that sort of follow from either this result or just some basic ideas. This result is used in the sense that, strictly speaking here, I've written decoupling as, delta needs to be 1 over an integer. Okay, one use that I love to use this identity for is that you can go through your proof and keep track of, delta needs to be 1 over an integer, and you get a bunch of these integrality conditions. Now, how do you prove this? But then you want a d of delta for all delta that's 1 over an integer, and your proof might force some extra integrality conditions. This is a useful thing. This is a good substitute for actually knowing this. Yeah, these tricks aren't usually directly used in any serious way, but they're good tricks to have in mind if you have some extra conditions. Like let's say you knew d of delta, a good estimate for d of delta, where delta is like 1 over an even integer. Okay, do you know d of delta for 1 over an odd integer? Well, then you can either use one of these two tools to get around it. They're useful in patching up these little conditions. Of course, you could redefine decoupling to not worry about being an integer or not, right? You could also not have these little sharp neighborhoods. Everything is negotiable in decoupling, as Terry would tell me. But yeah, these are little just functional tools that are useful to have when you try to prove decoupling theorems. Yeah, but they're not the main tool. Okay. So great. So we talked about parabolic rescaling, and now let's write our main theorem. Okay. So you've done the change of variables once, and then you don't have to do it again. As a consequence of this proof, actually the same change of variable says that even if, it basically says that decoupling problems are sort of translation invariant also. Like if I want to decouple this guy into interval size delta, the cost of that is the same as putting this interval at the origin and decoupling it into interval size delta. The same proof will work. It's just that it's easier. Okay. So the goal. Remember, our goal is to prove that d6 of delta is bounded by delta to the minus epsilon. Okay? And all the particular proofs have some sort of multilinearization. They multilinearize decoupling. The way they do it will, of course, vary depending on, so there are, of course, 3 proofs that I know of. There's the original Bourgain-Demeter 14 proof. That was a subset of the, of course, Bourgain-Demeter in 2014 proved this as a consequence of, well, they proved decoupling for the paraboloid, for which parabola is a subcase. There is the result of, there's the proof of myself that sort of proves the parabola case using ideas from efficient congruencing, and then there's the Guth, Maldog, Wong paper that used what's now known as, I guess, is more sometimes known as the high-low method, which shows that not only do I have delta to the minus epsilon, I actually have a log power, the power of log. And we're going to concentrate on these two. In particular, today, we're going to concentrate on this one. Because I think, me personally, I think this is the fastest proof, or the shortest proof. And so the way we bilinearize will be slightly weird. but it'll be convenient later. Okay. So, and actually, yeah, these two proofs multilinearize the problem differently. Yeah. Okay, so let's talk about how to multilinearize the problem. So we're going to let mu be a parameter chosen later, nu be a parameter. Chosen later. But we're going to think of nu as an intermediate scale. So we're going to think nu as being pretty large compared to delta, and I'm going to be vague what I mean with this. I mean just pretty large compared to delta, but also pretty small compared to 1. So nu throughout the proof, you should think of it as some sort of like, it should be like delta to the epsilon. Okay, and that will actually be our choice. So think nu is like delta to the epsilon. Okay, so now let's define our multilinear decoupling. So for integers a and b bigger than 1 and delta less than nu to the a and nu to the b, okay, let m a b delta nu. M for multilinear, really I could have called it b, bilinear. A and b depends on these parameters. It depends on delta and nu. Delta is our target scale. Nu is the intermediate scale. Okay. B, the best constant, such that, all right, let's write something. F theta I squared, F theta I prime to the 4 is less than m a b delta nu to the 6, sum partition I into delta intervals. And then we partition I prime into delta intervals. Okay, let me define notation for all f. For A supported in delta squared neighborhood of a piece of parabola of 0, 1. Okay, so for all f that lives here, it's a delta squared neighborhood. And so that this is standard. Okay, this is, we've always been working with this. And all I of length nu to the a, all I prime of length nu to the b. If we just have this, we've done nothing. This is as strong as regular decoupling. But in particular, with the distance between I and I prime separated. Okay. Remember, this tilde means that it's bigger than or equal to maybe 100, but we don't care about the 100. Okay. Actually, you could probably do greater than or equal to if you wanted. But yeah. So what does this say? Let's draw a picture. Let's try to understand what this decoupling constant says and how is it similar or different to the regular decoupling constant. Okay. Okay, so what does this say? Okay, so let's for the purposes of discussion for now, think of A to be kind of small. Okay, let's imagine A is 1 and B is 3 or something. Okay, so we have pretty large intervals here, right? Like delta to the epsilon is basically like 1, so we have like 2 intervals, delta to the 3 epsilon and delta to the epsilon. So we have 2 sort of intermediate but quite large intervals here. Let's lengthen 0, 1. So this is 0, this is 1. Okay, this is I, this is I prime. Okay, and what I want to do is I want to decouple. Let's draw a better picture. I want to break up this guy into intervals of size delta, and I want to break up this guy into intervals of size delta. Okay? So what does this decoupling constant measure? Well, it says that MAB is how much it costs to break up a function whose Fourier transform is supported here into its individual d delta pieces, but simultaneously. The idea is that you want to sort of maybe use some extra cancellation that happens between the interactions between these f theta i's and these f theta I primes. Because we have that these two intervals are very far separated. Nu is delta to the epsilon. This is basically an interval of size 1. Okay. So the idea here is that maybe we want to have, so for example, let's go back to the calculation we did last time. If we had an interval of a cap that's Fourier transform supported here, it's essentially, if the indicator function of this cap, right? What's the Fourier transform? Well, it's this dual tube. It's this dual tube. So this is let's say nu to the a by nu to the 2a cap. And then over here, we have a different direction. Its dual tube is pointing in a different direction. So therefore, these dual tubes have small intersection. So you want to sort of use some extra cancellation that comes from maybe the 2 and 4, or the interaction between these f theta i's and the f theta I primes. Okay. And these caps are sort of transverse, and sort of that allows us to have more cancellation. And we'll actually see that we'll actually need this condition. Yeah. Yes?
So you inequalize that there must be some summation over I
No.
inequality.
So MAB is the best constant such that this is true for all the choices of I and I prime that satisfy these three conditions. On the left-hand side? No.
There's no summation?
No. So MAB is the soup. So I compute the ratio between this and this guy, and I soup over all f, and I soup over all I prime, and all that satisfy this condition. Yeah.
Why do we choose these moment?
Yeah. So the Bourgain-Demmin argument will almost choose 3 and 3, and this seems more natural. But the 2 and 4 is actually more convenient. Mostly the 4 is not important. The 2 allows us to use Plancherel. There is a sort of key estimate that we'll talk. There are a series of key estimates. One will be the most key estimate. That key estimate, if you choose 3 and 3, you'll have to use some sort of bilinear K argument. But if you choose 2 and 4, you can get by with just Plancherel. And we'll talk about that in a little bit. This is unnatural, but it does allow you for a shorter. It is more natural later in the proof to do. Yeah. But basically, you have a bilinear decoupling to take advantage that there's going to be more cancellation. There's going to be more cancellation. There's going to be more cancellation interacting between these theta I and theta I primes. Yeah. Okay, great. Now, of course, so it's asking how much does it cost to simultaneously decouple these two caps into intervals of size delta? If I knew how much it cost to decouple anything into intervals of size delta, then of course I would be done, right? So if I knew how much it cost to decouple something into intervals of size delta, then I would know how to simultaneously decouple things into size delta, because I would just pretend this guy doesn't exist, decouple this guy into delta, and then suddenly I'd pretend this guy doesn't exist and decouple this guy into size delta. So morally, this would say that if I know regular decoupling, then I know how much it costs to decouple to bilinear decoupling. Of course, I don't want that, right? I want to imagine that MAB has more cancellation because I have this extra spacing which allows for transversality, and my tubes point in different directions, and so on and so forth. And so I want the reverse. I want to know the fact that if I know how big MAB is, then I know how big DP is. Right? I want bilinear decoupling to control regular decoupling. So that's what we're trying to prove here. Yeah. Yeah.
In the end, there's still parts that, for example, I equal to I prime.
And we'll have to get rid of those. Yeah. So usually these arguments go with two parts, right? So either, as you said, so either I is equal to I prime. But if I is equal to I prime, that's f theta I to the 6. And that's dp at a bigger scale. So that's good, right? Because I've broken up the problem into an easier problem. Or I have what's called transversality. That's called the broad piece. We'll talk about them in a little bit. Okay, so let's also talk a little bit more about this bilinear decoupling first. So how should we think of the parameters a and b? A is some integer, b is some integer. As long as delta is less than nu to the a, nu to the b, this is well defined. Right? Like that's the easy condition. I'll often omit it because just writing this statement means delta has to be less than nu to the a. Otherwise, it doesn't make sense. So if a and b are large, then I really haven't done much, right? Because this is like saying I'm bilinearly decoupling two large intervals of size delta. I really haven't done anything, right? Because the main problem is to break up this whole interval in terms of size delta. If I have delta to the epsilon size interval, I've done nothing. Okay. But if a and b are so large that, let's say, nu to the a is 5 delta and nu to the b is 10 delta, like if it turns out that this guy is 5 delta and this guy is 10 delta, then I'm basically done up to constants. I don't care about 5s and 10s. Right? Then I'm basically done because I can just break this up into 5 different pieces. Okay, that costs, $1 million. And then this guy has 10 pieces, so I just break it up into 10 pieces, and that maybe costs another $1 million. Okay, really, it costs like 5 and 10 or something. And then I'd be done. Right? So what is the goal here? What is the game here? We want to go from small ab to large ab. And we want to do it efficiently. Okay, so there are going to be 2 key estimates. One key estimate that controls d of delta by essentially m at a small ab. Right? Because small ab means that I really haven't done much. These are still pretty large intervals. Okay, it says that dp is morally basically controlled by m at a small ab, plus some, as Guodong you mentioned, plus some diagonal term. Okay, that is good. And then the second step will be that now we've reduced the problem to studying m at a small ab, and then our next step will be to increase ab so that ab gets larger and larger. Of course, you could trivially break up, some interval of size delta to the epsilon into intervals of size delta, but that just using Cauchy-Schwarz. But that's really bad. So we need to think of a way to do this efficiently, and that's where this 2 and 4 this 4 is actually not so important. The 4 is only there because it's 6 minus 2. The 2 becomes extremely efficient to use. Okay? Yeah. Maybe we take, since it's 49, maybe we take a slightly early 5-minute break. And then we start with the bilinear reduction first. Yeah. Yeah. Or we can continue asking questions.
So then you mentioned you choose the exponent 2 and 4, and eventually you are, maybe for some terms, just simply use differential.
Yeah, so the key we have this multilinear constant that allows us to sort of take advantage of potential extra cancellations between f theta I and f theta I prime. And the idea is to reduce, we have this object that we have no idea how to control, and we want to reduce to something that we have a better idea of controlling. At least there's a better hope because there's more cancellation. Anything that has more cancellation that we can exploit, we should. Right? So we have the bilinear reduction. Okay. So bilinear reduction. Okay. Okay. I guess in my notes I have a small remark. Here's an exercise. And this is a remark saying that if I know dp is small, then I know mab is small. So how do you quantify that? Exercise. mab of delta nu is less than dp of delta over nu to the a to the 1/3 times bp of delta over nu to the b to the 2/3. Okay, so what does this inequality say? If I know that dp is small, then mab is small in a quantitative way. And the proof is just,
Holder?
huh? Yeah, it's just holder. It's literally just this holder. 1/3. Yeah, and then 2/3. And then apply the definitions. Okay, so that's also a nice exercise. But it's just holder. So this says, if I know dp is small, then I know mab is small. This is the sentence that goes along with this estimate. But I don't want that, right? I don't know anything about this, so why would I know anything about that? Okay, I want the reverse inequality, and that's bilinear reduction. So it says that d6 of delta, sorry, I keep on messing up the dp's and 6's. P is always 6. Yeah. d6 of delta is bounded by, and this is like, you know, a million. Okay. d6 of delta over nu plus nu to the bounded constant, and you can work this one out, I believe this is like 3 or something, times m11. Okay. So this first term indeed, as Guodong you mentioned, this follows just from the diagonal case. And then this is the bilinear term. Okay. Now, so how should we think of this inequality? So let's imagine that this term wasn't here. Well, let's imagine this was always the dominant term. Okay. This is good. Why? Well, nu is like delta to the epsilon. Right? So what is this saying? This is like saying d6 of delta is controlled by d6 of delta over a larger scale. And if it was always dominant, then I could just keep on going. Right? I could say, well, maybe like it's like d6 of delta to the 1 minus epsilon is bounded by maybe d6 of delta to the 1 minus 2 epsilon, and then I keep on going. And then, you know, maybe one day I'm going to get up to d6 of 1/2, and I know how big d6 of 1/2 is. It's just size 1. All right? So if this is the dominant term, this is a good term. Right? Now, if this is the dominant term, then that's also good, because then what we've done is we've just said d6 of delta is controlled by m11. Right? D6, the regular decoupling is controlled by bilinear decoupling. So therefore, it suffices just to get really good estimates on m11. Okay? So where's the eraser? So yeah, so this is and there's always, in all the decoupling proofs known so far, is that there are some, you know, so the proof that I will give will also just follow from holder and looking at diagonal, off-diagonal terms. Later, we'll talk about a broad narrow argument that works in higher dimensions. But there's always some sort of lemma that says regular decoupling is controlled by, this is called the broad term, or this is called the narrow term. The narrow terms, just telling you the terminology, and then this is called the broad term. Okay, there's always some sort of broad narrow decomposition that sort of sorts the problem into two cases. One case that just sort of follows is like a rescaling. You've rescaled the problem to go to a larger scale, or you reduce the problem to a larger scale, plus some term that has some sort of transversality, some extra cancellation that you want to use that makes the problem easier. Okay, so we've made the problem easier, right? It says that the problem that we want is reduced to the problem at a larger scale, which is good if we can do that consistently, plus, or the problem is reduced to a problem that has more cancellation that we can use. Okay? Okay, so how do you prove this? In the parabola case, it's particularly easy. And it just follows from holder, so let's do that. Okay, so proof. How do you prove something about the decoupling estimate? Well, you need to start with this left-hand side. Okay, raise everything to the p power first. And then you need to have a right-hand side that looks like this. Okay? And then you want to show that basically the LP norm of f is controlled by this right-hand side this right-hand side times by this guy. And then since dp of delta is the best constant you can put here, that means dp is less than this expression over here. Okay, you're just playing with the definition of best. Okay, so proof, you start with the left-hand side. Okay, and what's our target? Our target is, okay, so M11. What's the definition of M11? I take two intervals of length nu in 0, 1, and I want to see how much does it cost to simultaneously decouple them into intervals of size delta. So what do I want to break up f into? I want to break up f into intervals of size nu. Look at diagonal terms and then look at off-diagonal terms. Okay. So this is great. So sum I prime in p nu f theta I prime squared, or cubed. Cubed, yeah. Right. Right, and then what do I want to do? A diagonal and off I is equal to I prime or not. Right, so then of course, maybe we lose some constants here. Then we break up into the case when I is I prime. Okay, maybe we put 1/2 times 6, or it's not. Right, just diagonal, off-diagonal terms. Right, now what do we do? Let's call this A, and let's call this B. Okay. Let's. Okay, let's control A first. A. Okay, A is, let's bring the absolute value inside all the way in. All right, so what is A? So A is less than the integral of sum I in p nu f theta I squared to the 1/2 times 6, right? And so this is like an L6 normal on the outside. I do first little L2 and then big L6. So you can interchange these by Minkowski. You can first do L6 and then do L2. Okay, so by Minkowski, this is then less than sum I and p nu. So you first do 6 and then do 2. Minkowski. Okay, and that's great, right? This is good because what have I done? I've broken up. This is my original problem. I've broken up my problem into intermediate pieces, and I know what to do there. At least if I know how big decoupling is. I rescale each of these pieces, right? So then this is less than sum I in p nu d6 of delta over nu times sum j in p delta of I f theta j L6 squared 1/2 times 2 to the 1/2. Or if you don't want to read that, this is just equal to sum j in p delta times by f theta j L6 squared to the 5 times 6. Missing some 6's. 6. There's some 6 here. 1/2 times 6. So this is 6. No, there's no 6 here. d6 of delta over nu to the 6. Okay. So what you do is you basically apply the rescaling lemma to this guy, plug in what you get, and you get this. Are there any questions? I mean, up to some algebra here. Right, so go from here to here, parabolic rescale. Okay. So that at least explains the first term. Right, that at least explains this term. Now, how do we explain the second term b here? Okay. Well, to explain the term b, for b, we do something really trivial. See, nu we're going to think in the end to be delta to the epsilon. So we can lose actually bounded powers of nu. That's okay. Right? So what we're going to do, well, in this sum over here, there are nu to the nu squared many terms. And then I raise it to the 3, so there's nu to the 6 many terms. Anyways, there's a bounded power of nu inverses that occur. So I'm going to union bound. I'm just going to take the worst guy. Okay? So union bound, and this is less than nu to the bounded times the maximum over I and I prime in P nu, distance I and I prime bigger than nu, times the integral of f theta I cubed, f theta I prime cubed. And of course, this is the natural point to stop, but our bilinear decoupling is not 3-3 based, it's 2-4 based. How do you go from 3-3 to 2-4? You hold her. Okay. So then, well, what do you do? Well, then this is controlled by nu to the bounded, max I and I prime in P nu, distance I and I prime is at least nu. Okay, so what's holder? Well, it's just this. Okay. Now, the maximum of this is, of course, controlled by the maximum of this guy times the maximum of this guy, which is the same maximum because I and I prime are symmetric here. So then, of course, this is just equal to nu inverse, nu to the minus big O of 1 times the maximum I prime times that guy, because I and I prime are symmetric. I guess I'll write a less than or equal to be safe. Okay, and then what do I want to do now? Well, I want to see the decoupling right-hand side, right? I want to see this right-hand side. So what do I do with this guy? Well, I just apply the definition of what? Well, I remember I and I prime are intervals of length nu, and they're nu separated. That's exactly this condition over here with a and b equal to 1. Right? This is MAB was designed for nu to the a and nu to the b. But here I'm using when a and b equal 1. I and I prime are intervals of length nu. So that's where the definition M11 comes from. So let me write that down. So then this guy is less than bounded max I prime P nu distance I prime is at least nu, okay, times M11 delta nu to the 6 sum j and I, oops, j and p delta I. Okay, so I've just inserted the definition of m11 to the 6. Great, but let's pause for a moment. Well, nu is like delta to the epsilon, so this sum is like, probably 95% of the terms anyways. And this is also like, another 95% of the terms. So we're just going to do something trivial and just control this by nu to the minus bounded, m11 delta nu to the 6. And this is just inside 0, 1, so let's just kill it all. J and p delta 0, 1. There. Right, so what have we done? We've shown that the L6 norm of f is controlled by two terms. The narrow piece, which is d6 of delta over nu, this is a larger scale, times the regular decoupling right-hand side, plus the transverse piece, the broad piece, which gives this contribution times by the decoupling right-hand side. So now we use the definition of decoupling, and then we put a d6 on the left-hand side and take 1/6 powers. Okay, now use definition of d6. Okay. And so the moral of the story is that we've controlled d6 of delta by d6 at a larger scale. This is always good. This is the not significant piece, plus the multilinear constant. So this reduces effectively, this doesn't necessarily reduce the problem to a multilinear problem, but given that this term is almost always the nice piece, this effectively reduces studying d6 into the multilinear piece. So now we just need to concentrate, how do we upgrade from small a and b to large a, b? Right. And morally, this is reasonable because, essentially, this is like me saying that, well, I don't know how to decouple the whole interval. Well, so what I'm going to do is I'm just going to take, two large intervals that are, at two ends of 0, 1. One that's close to the origin and the other is close to 1. How much does it cost to decouple these large interval size delta? This is this morally feels like the same problem, right? The only thing you've added in is a little separation. And the separation, the ability to add in the separation is this bilinear reduction of the broad narrow argument. Yeah. This is a more baby form of the broad narrow argument in that it only relies on Holder. The actual broad narrow argument due to Bourgain and Guth is much more complicated, and we're going to talk about that later. Yeah. Okay, any questions? Okay, so now that we're going to have a key estimate. So now we need to think about how do we go up from M11? And actually, so we don't necessarily have to start at M11, right? You can go, so what is M11 again, right? It says take two intervals of length nu. Let's say one's at near 1, one's at near 0, and the other was near 1. And I want to break these up in interval size delta. Okay, and I pay a cost of nu to the minus 10 here. Of course, I don't have to start with 1, 1. I could start with 2, 1 or 2, 2. As long as I can start with any integer. As long as I start with a fixed starting point, I pay a cost of big O of 1, that's fine. Right? I could trivially break up nu into nu squared, paying a cost of nu inverse. Right? That's fine because nu is delta to the epsilon, so I pay a bounded power of delta to the epsilon. That's fine. Right? Okay, so starting at 1, 1 is not so important. It's that we start somewhere. We start at 10, 10, a million. That's fine. The idea is that we need to go up to 1 over epsilon or something. Okay, so what's the efficient way to go up? Let's see, which board to erase? Let's erase this one. Let me write down the key lemma. That turns out to be the efficient way. Okay, so the key estimate. It turns out to be if 1 is less than A is less than B, then MAB, so there needs to be a way for MAB to climb up efficiently. Okay? It turns out that the efficient way to climb is, okay, so I'm going to lose the bounded power of Newton. That's okay, this is delta minus epsilon loss, times by M 2BB. Okay. This turns out to be the efficient way to win. Okay. Let me prove this estimate, and then we'll go through the iteration. So the rest of the rest of how I'm going to present is that I'm going to present this estimate, and then I'm going to show the iteration, and then you'll see that we win. Now, how do you know ahead of time that you win? You don't. If you sort of try to see what you can prove, and then maybe you're able to do like 3 halves. If you try this method for the paraboloid, and then you'll realize that maybe sometimes you'll have some intermediate results, right? And then you're like, oh, I can do this, and then you try to iterate, and you realize it's not enough. Right? So I don't think I can give so much of a strategy as to sort of how do you see ahead of time, why this is the case, other than just pure experience and trial and error. It's very similar to how, if you look at the Bourgain-Demeter-Guth proof of Inequalities, it's a very complicated iteration. And you can, at least when I was reading it, I was sort of wondering, it's like, wow, how did they create this fancy iteration? And I'm sure it's just a lot of trial and error. And certainly on Woolley's proof of Inequalities, my impression is that Woolley also tried a lot of different iterations and finally got the one that worked. So a lot of this is you try to prove what you can, and then you test out your iteration. Sometimes it works, sometimes it doesn't. Usually there is going to be some expression that all these proofs just barely work in some sense. If you make this quantitative, there's always going to be some expression that is basically equal to 1 or tends to 1 at some point. And there's always some matrix lurking in the background that has eigenvalue 1 to allow this. There is some discussion. If you look at various notes, for example, Terry's notes on decoupling, there's some discussion about how behind every iteration there's some matrix, and this matrix needs to have eigenvalue 1 to win. Sometimes you'll have matrices that have eigenvalue 0.99. Of course, that's not good enough. Yeah, basically because you have a matrix, you raise it to an arbitrary large power. If your eigenvalue is 0.99, this doesn't work. But if it's 1, then you win. Yeah, there's some discussion on the various things that I've linked to this, but we won't discuss that. But this turns out to be the right estimate. Okay, so why, or if I wanted to prove this estimate, how would I prove it? Well, I mean, just like how this estimate, had some, actual estimates about integrals behind it, and we had to if we proved the resulting integral estimate, we could prove the resulting decoupling constant estimate. What is the estimate behind this guy? Well, this key estimate will follow from the fact that the integral of f theta I squared, f theta I prime to the 4 is bounded by some and there's some conditions for all I of length nu to the a, I prime of length nu to the b, distance I and I prime, at least nu. And of course, f is for a supported in a delta squared neighborhood of a piece of parabola above 0, 1. Okay, so what does this estimate say? Let's first digest this estimate, and then let's talk about why this estimate implies this guy, and then we'll talk about this proof, which follows from Plantrell. Okay, so what does this estimate say? Here are going to be two intervals. I is of length nu to the A, I prime is the length nu to the B. Okay, and they're nu separated. Okay, so we have two sort of medium-sized intervals. They might be the same length, right? We do allow when A equals B. If you don't like, thinking of too many parameters, you could set A equals B. The proof is the same. Okay, A equals B is usually the critical estimate. Okay, so we have sort of two intermediate intervals. They're basically the same length, or they're close in length. But the point is that they're very far separated apart. Right? The distance between I and I prime is the length nu, and you have to think of nu to the A and nu to the B as, pretty small, but not, nu to the A is like, a billion and B is a billion. Okay, so it's much smaller than nu, but like it's still much bigger than delta. We're like in the intermediate stages. Okay, and what does this say? Well, this says keeping these four pieces constant. These four pieces show up on both sides. We can decouple I into intervals of length nu to the 2b. Okay, so what does this say? Here's I prime. Here's I. Okay. What does this say? It says that, I can, with this term here, I can decouple this piece into intervals of length nu to the 2b. And this turns out actually to be the right scale to decouple. Okay, so that's what this says. And from a number theory perspective, this is also a reasonable estimate to do for the same reason that I pointed out during the break. If I knew these four variables and I kept them the same, then this would tell me very strong diagonal behavior about x1 and y1, right? And so that's almost what this says. I keep these things the same on both sides. This tells me very strong diagonal behavior at a certain scale about these two pieces, right? Sort of some connections. Okay. Are there any questions? Okay, so great. So if we have this estimate, why does it imply this? Let's answer that question. So if we knew this estimate, why does this immediately imply that MAB is less than that times nu M2BB? So, okay, so let's ignore the bounded powers of nu. Okay, and let's also raise everything to the 6th power. Okay, where does the 2BB come from? Where does the AB come from? Okay. Okay, so if we knew this estimate, if we knew star, then, okay, so what do we have? The integral of f theta I squared, f theta I prime squared 4 is bounded by nu to the minus big O of 1, sum j in P nu to the 2bi of this guy. Okay? This is of length nu to the 2b. This is of length nu to the b. J is an I. I is separated by I prime by a length nu. So therefore J and also I prime is also separated by a length nu. Right? So let's apply the definition of M2BB to this integral here. Right? So now apply the definition of M2BB. We get M2BB delta nu to the 6. Let's be a bit sloppy and let's just write this. Okay. Times by, okay, so now what do? We want to do, we have the first interval gets partitioned into intervals of size delta. And then the second interval in this integral, which is I prime, gets also partitioned into intervals of size delta. Okay? So I've just applied the definition of M2VB. Now I'm going to take this out. And the point is that this is a power 1. So this sum only attacks this guy, right? This sum is independent of this guy. Right? There's no j in this sum. So therefore, what do I get? I get that this is nu inverse sum j in p nu to the 2b of I sum j prime in p delta of j f theta j prime. Okay, and then times by j prime prime right, and I'm going to put a 1/2 times 2 here. Right, I'm purely using the fact that this is 1, so I can just combine these two sums into this guy. And then this sum doesn't attack this guy anyways. I'm going to pull it out. Great, but that's convenient because this is just one sum, right? I'm summing over all the j's in I of length nu to the 2b, and in each of these j's I'm going to sum over all the interval size delta. Well, that's just summing over interval size delta in I. Right, so this guy is equal to the sum j prime in p delta of I. But that's literally the definition of MAB. Right, this is the right-hand side of MAB. Right, this is the right-hand side of MAB. And then now we apply the definition. Now apply the definition of MAB delta nu to the 6 to finish. Right? We just showed that, I guess I'm missing a so this is M2B, B to the 6. We just showed that this guy is bounded by this constant times this guy. Well, this is the left-hand side of MAB. This is the right-hand side of MAB. MAB is the best constant that I can put here. So therefore, MAB to the 6 is bounded by this guy. So therefore, I would get that. So this is the key estimate proof. Yes?
So even though the power is not like 1/2 times 2, as long as it's bigger than 1, you still can use string inequality.
So in higher dimensional cases, so for example, in the proof of decoupling for the moment curve, you won't get a 1 here. You'll get some higher powers, and it turns out that you use Holder and Minkowski, and it all works in your favor. Yeah, which is somewhat of a mild miracle, but yeah. It's just that in the parabolic case it's equal to 1, so it becomes easy. But for the moment curve, you play a similar strategy, in that you want to prove some estimate about MAB and stuff like that. It turns out you just need to prove this, and the proof is just something like this, and you have to do some Holder Minkowski type things. Yeah, and then it works. Yeah. Good. So we have to just prove this. Are there any other questions? Okay, so let's prove this. Okay, let's erase this board. Okay, we'll keep this one. Which one? Let's erase this board then. Okay. Good. So I said that this follows from Plancherel. Now it's not obvious that it follows from Plancherel. Right? It's not literally, I just take hats on both sides and it just comes out. But it almost does. Okay, so there are going to be a few proofs of this. There are actually a few proofs of this estimate here. One proof I can tell you is, it uses the fact that both 2 and 4 are even. I expand everything and I look at things very carefully. I expand, I go all the way down to looking at the Fourier transforms and looking at how the frequencies interact. Okay, that's one proof you can do. The second proof you could do is more similar to the Bourgain-Demeter proof, and it uses what's called wave packet decomposition. So, like in the first lecture, we computed how 1 theta I, how 1 theta I looks like you can do a similar sort of computation and sort of almost see what the f theta i's look like. And essentially they look like sort of linear combinations of sort of dual boxes. Okay? And then what you do is, well, you have one dual box going this direction, the other dual box going in another direction, and you say that you use bilinear cocea and they have small intersection. That's very similar to the Bork-Demeter style. And we'll talk about that in the next lecture, because that will introduce the uncertainty principle. But just so that we actually have a decoupling theorem, let's give what I think is the simplest proof, and this one follows from Plancherel. And so there are varying proofs of this, and it's useful to compare and contrast the ideas. The Plancherel proof, I think, is the nicest, but it's the one that I think applies in less settings, but it's the fastest one. Okay, so what do we do now? We want to prove this estimate. Great. So what's the picture? All right, so I'm drawing pictures all over the place because pictures are sort of the driving force of how to prove these estimates. You don't prove these estimates blind. Okay. Great. So what do we know about I and I prime? Well, I mean, maybe I lives here and I prime lives here. Okay, and this is pretty big. Okay. Now, by the same proof as parabolic rescaling, you can always shift I prime down to the origin. And of course, you shift I, you just shift the problem completely down to the origin. You can do that, and the proof of that is the same as parabolic rescaling. Okay, you just don't dilate it, you just translate it. Okay, and I won't do that proof because it's the same computation. Okay, so by the same argument, as parabolic rescaling, okay, we may assume that I prime is at the origin. Okay. Just do the change of variables. And it's purely because I want to prove this estimate for all f whose Fourier transform is supported inside a delta squared neighborhood. Okay, use the fact that this is for all f. And so then you can use the fact that I prime is centered at the origin. Yeah. Okay. Now, so what do we want to show? We want to show then that the integral of f theta, and I'm going to be explicit, d comma d plus nu to the a to the square times f theta 0 nu to the b to the 4 is bounded by bounded power of nu sum j partitioning the first interval into intervals of size nu to the b. And the other 4 copies stay the same. Okay, and this is for all f with Fourier support in a delta squared neighborhood of the parabola above 0, 1. Okay, so we want to prove this estimate. Right, so to see this, you just say, well, I want to do that problem. You do your same change of variables. You literally say, well, you write I prime as e comma e plus nu to the b, and then subtract e. And then your change of variables will say that you want to prove this estimate for all f. Okay, so you shift to the origin. Okay, so we've done nothing, pretty much, almost nothing. Now we want to do something. Okay. So we want to use Plancherel. I mean, this is like, if these 4 terms weren't here, it's like, oh, maybe it's useful to try to do Plancherel. But now we have to do these 4 terms. What do we do with these 4 terms here? Well, let's rewrite our estimate. Maybe we keep this one. Okay, so let's start at the left-hand side. Well, we're just going to use the fact that we have a 2 here. So let's, so this almost says that I want square root cancellation. Well, this says that I want square root cancellation in these guys, right? Assuming that we have these 4 pieces over here, right? So remember that f theta d plus nu to the a, of course, is equal to right? Because where's the eraser? Let's draw a picture. Here's my interval d comma d plus nu to the a. I partition it into intervals of size nu to the 2b. I'm Fourier supported in the delta square neighborhood of the parabola. You can imagine that it's very small, so let's imagine it's the thickness of the chalk. Okay, so f theta d comma d plus nu to the a is this piece. This color. This is this piece. Okay. And then what do I want to do? Well, each of the f theta j's are just these pieces. Are just these pieces. Right? So this is a true identity. Okay? And so this is like saying, well, I mean, so what I'm going to do is eventually I want to at least see this sum up here. I want to see the sum in j's up here. So let's just use this true identity, plug it into the square. Let's just deal with it, right? Like we're basically asking for square root cancellation in this sum, subject to these 4 powers of f thetas, right? So I mean, I just literally said square root cancellation, so that should be Plancherel, but there's something weird. There's something funny about these 4 powers that we need to take care of. Okay, so let's put the sum in. J, okay, and then let's take this out too. Let's write squares here. These are equal, right? And now it's an L2 norm. So let's do Plancherel. So what does Plancherel say? And let's do something that you can only do on a chalkboard, that erase and rewrite it. Right? All I've done is Plancherel. Okay, so, let's to be precise, let me do it slower, and then I'll write it again. Okay, so what was the intermediate step? Squared, and then of course then Plancherel. What does this say? Well, okay, so now I'm sum j f theta j hat convolve f theta convolved f theta. Right, this is just Plancherel. Okay. Now, what do we want to do? Well, if these guys were if these guys were orthogonal to each other, what would happen? Well, if these guys were orthogonal to each other, at least if they all had disjoint support, I could bring the absolute value inside, interchange the sum and the integral, undo Plancherel, and then I would be left with the right-hand side over here. Right? If these supports were if these supports were disjoint, then I could say, well, okay, well, I just expand the square, and the supports are disjoint. So for each j, it doesn't touch any other j's. Then I would apply, and then I undo Plancherel, and then I have the right-hand side. So what's the plan? That's almost the plan. Except that if that was true, if for each j the support doesn't touch its neighbors, then I wouldn't have a nu to the -1 loss here. Okay. But if for each j it touches nu inverse many neighbors, then of course by enough Cauchy-Schwarzes, then you lose a nu inverse bounded power, I don't care what it is, times by the diagonal contribution. Okay? So that's what we're going to try to aim to do. We're going to study, as j varies, what do the supports of these look like? How many, given one j, how many supports does it touch? Okay. We count them. It turns out that it will touch about nu inverse many, nu to the bounded many. And so therefore, by almost orthogonality, then I'm done. Okay. So now let's draw. So behind every decoupling proof, there is a geometric picture. This will be the geometric picture. What do the supports of these guys look like? Okay. So let's draw the supports. And here we'll really need the geometry of the parabola. The geometry of the parabola is really used in this lemma. I mean, strictly speaking, parabolic rescaling, okay, it's just calculus, and you don't have to actually see the parabola. But here we do really need the geometry of the parabola. And we'll also need the fact that our things are transverse. In other words, I forgot to say here, this parameter d is at least nu, because these two intervals are at least nu separated. We're going to actually use the transversality, and we're actually going to use the geometry of the parabola, okay, in a serious way. Okay. Let's draw the supports of these functions. Okay, so let's study the support of f theta j hat convolved f theta 0 nu to the b convolved f theta 0 nu to the b. Okay, and j, what is j? J is an interval of length nu to the b inside this interval of length nu to the a, and the length is not so important, but at least it's how far is j away from the origin? It's at least nu far away. So here's 0, here's 1. Here is d comma d plus nu to the a. J lives here, and this is at least nu. Okay. Okay. If you don't like nu, you can think of, for the geometry part, if you don't like to think about nu, you can think of nu as 1. I mean, nu is delta to the epsilon anyway, so you can pretend nu is 1 if it makes life easier. Okay? Just for the geometry portion. Okay, so let's draw a big parabola, and let's look at where is this supported. Okay. These two pieces, it's easy to see where it's supported, right? What is theta 0 nu to the b? Well, this is the piece of parabola that lives above 0 nu to the b, and it has thickness delta squared. Okay, so it sort of lives here. And I actually don't need delta squared thickness. It suffices just to actually assume that this is nu to the 2b thickness. You can write delta squared if you want, but the piece of parabola that lives above, so it lives in this tiny neighborhood. For convenience, we can actually thicken it a little bit by pretending that it's a rectangle. So my point is that imagine delta squared is the thickness of the chalk. I start seeing the curvature. At what scale do I need to thicken this neighborhood of the parabola to not see the curvature? Well, I should pick the length squared, right? Because if I travel in the x direction from 0 to nu to the b, how much has the curve gone up? Well, it's gone up by nu to the 2b. So the piece of parabola that lives above 0 nu to the b has only gone up. It lives in a box of size nu to the 2b by nu to the b. Okay? And that's the natural scale that this sort of piece lives at. Okay? So this curve lives at a scale of size nu to the 2b. And we're actually only going to look at the projection of this support onto the y-axis. So even if you were to really look at the delta squared neighborhood of this piece of parabola, it still lives in a strip of height nu to the 2b. Okay, so this guy lives inside this strip centered at the origin of height nu to the 2b. Okay? Where does J live? Where does J live? Well, this is 1. Okay, and J, okay, so this is D. This is D plus nu to the A. J lives here. Okay, J is of length nu to the 2b. Okay, so where does f theta j live? Well, f theta j, I lift it to the parabola. It lifts inside this nu to the b by nu to the 2b thickness box. Okay. Strictly speaking, it lives inside a delta squared by nu to the b box, but at that scale I see the curvature. At what scale do I not see the curvature? Well, it's nu to the 2b. Okay. Now, how tall is this box? How tall? Basically, as I've gone this way by nu to the 2b by nu to the 4b. This is of length nu to the 2b. If I've gone this, how tall is this box? Well, you can compute it. You can literally compute this point and subtract this point and bound everything. What's the quick and dirty way to see this? Well, you look at the slope, right? So what's the derivative at this point? Well, the derivative is just, at least 2d. Is basically, the nu to the a is very small. So the derivative, the slope of this curve, the slope at this point is like 2d. So I've gone this way nu to the 2b. So how much do I go by? Well, I go by d times nu to the 2b. We don't care about constants. This is where the tilde and the constants come in. So basically, this rectangle is height d times nu to the 2b. Okay? And so, what is the strip? What does the y projection look like of this strip? Well, it's a strip. Okay, so let's look at the vertical projection of this strip. This is a strip of size d nu to the 2b, and it's centered. Where is this centered at? Well, it's basically centered, so I'm going to call this Cj. So this point here is Cj comma Cj squared. And so this strip is basically C1 comma C2, such that C2 is Cj squared plus big O of d nu to the 2b. Right? Okay. Are there any questions so far? Okay. So now we know where this guy lives. This guy lives in the red piece. And then this guy lives in the white piece. So where does the convolution live? Well, this is a strip centered at the origin. So I'm just going to take this guy and maybe dilate it by like 10 or 5 or 2. Right? So the convolution lives inside this dilated piece. And what is this strip? Well, this strip is still a strip of size C1 comma C2, such that C2, it's centered at Cj squared plus a slightly bigger constant of size d times, a slightly bigger constant, but now this strip is, so this strip is a height nu to the 2b. This strip is a height d times nu to the 2b. Now d is small. I've drawn this picture slightly off. D is small. D is a number between 0 and 1, and this is a strip of height nu to the 2b. So this is like d plus 2, right? So the dominant term is the 2, the plus nu to the 2b. Right? I'm just adding the supports. So this is of height 1, this is of height d. So when I convolve them, it's of height d plus 2, and so in other words 3. Okay? So this is this strip. Okay. So for each j, the supports of these guys live in a strip that look like this. Okay? And we can make this explicit. It's like 3. Okay? It's the strip that's contained by C2 minus Cj squared is less than or equal to 3 times nu to the 2b. Okay. So for each strip, it lives in a strip that looks like this. Now we have to ask, as j varies inside this interval, how many strips does it, to each j here, it corresponds to one blue strip. The blue strip is given by this equation. So as j varies, how many of the other blue strips does it touch? For each j, how many of its neighbors does it overlap with, and how often is this overlap? Okay. Now, so now we just have to compute something. Okay. Where is the space? Okay, so let's call the strip Sj is the strip corresponding to the support of this guy. Okay, so given a j, how many of the other j primes does it intersect? Well, if Sj intersect Sj prime is not equal to empty, if it's non-empty, then if two strips have non-empty intersection, then that means the centers squareds are within nu to the 2b of each other. Then, okay, but let's look at difference of squares. So what does this say? Remember, this says that the absolute value is less than a constant times nu to the 2b. So in other words, this is shorthand for absolute. Okay, shorthand. Okay, so in other words, absolute Cj minus Cj prime is less than nu to the 2b divided by absolute Cj plus Cj prime. Okay. Now we still haven't used one thing yet. We haven't used that my interval over here is at least nu away from the origin. We have not used the fact that j here lives at least a distance nu from the origin. In fact, all the j's we care about in this calculation are at least a distance nu from the origin. So therefore, we have a lower bound for Cj and Cj prime. So happily, we get that this is nu inverse times nu to the 2b. So in other words, if two strips interact, their centers must be at least within this distance apart. Or in other words, if two strips interact, the strips must be within like like if I count them, it must be within new inverse many intervals apart. So each of these strips, the corresponding blue strip, only infects new inverse many of its neighbors. Okay, fine. So then, up to a constant nu to the minus big O of 1, I can have almost orthogonality over here. And that's leave as an exercise in Cauchy-Schwarz. Okay? And so then I'm done. Yeah. Okay, and then, so that's the key estimate, and I'm almost out of time, but let's introduce one last estimate. So what have we proven? What are the estimates we've proven? We've proven that D6 is controlled by D6 at a larger scale plus, okay? This basically says that regular decoupling is controlled by bilinear decoupling at sort of a large scale, which sets the iteration beginning. The second is a key estimate, which says that if A is less than B, then MAB is less than delta to the minus epsilon times MB2BB. Okay, and then there's a third estimate. So I've only increased the first index, right? So what does this say? Let's apply it already to one step here. This says M11 is controlled by M21, which of course I would know trivially, right? But you can imagine that, you know, MNN is controlled by M2NN for n large, with a control of that's bounded, right? Of course, the trivial bound if MNN is nu to the minus n, but here I only lose nu to the minus 5 or something. Okay, so this allows me to increase one of the indices. What about the second index? Well, we have the following identity. MAB of delta nu is less than MBA of delta nu to the 1/2 times D6 of delta over nu to the B to the 1/2. This allows us to interchange the gain in the first index and move the gain in the first index to the second index, because let's see what happens. M and N, so let's trace what happens at one step. Let's say M and N, okay? And I use step 2, and it goes up to M2NN efficiently, okay? And then what does this say? Well, this says, okay, up to, let's only talk about schematically. Let's ignore the 1/2, and let's ignore the 1/2, and let's ignore this D here. Let's only talk about which multilinear constant it affects. Okay. Now let's interchange these two guys. So step 3, so step 2 allows us to upgrade the first index. Step 3 allows us to move to MN2N. And then what we do, well, now we're back down to here. Right? The first index is less than the second index, which means I can upgrade the first index to twice the second index, which allows me to go to M4N2N, using 2 again. And then this is how I climb the ladder efficiently. Now, how do you prove this? Well, you use holder. The particular holder you use is f squared g to the 4 is less than f to the 4 g squared to the 1/2 times g to the 6 to the 1/2. Right? Because 4 times 1/2 is 2, and then 1 plus 3 is 4. Okay? And I'll leave that one as an exercise. And so next time I'll finish the iteration. I'll do the iteration ignoring these less than tildes. And I might also ignore I'll keep the new inverses, just so it makes the iteration cleaner. And then what we're going to do is we're going to talk about the uncertainty principle and how one would prove this estimate in the style of Bourgain and Demeter. Okay? Yeah. All right. Are there any questions? Yes?
So can we imagine how kinds of iteration we want?
As in, how do you know if an iteration works or not?
Try it.
You just try it. Yeah. 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 The current method, there's no sort of big theorem that says, like, if I prove these estimates, then I will win. The current techniques all are, I think the way everyone does these things, at least as of right now, the state of knowledge right now, is that we usually this step, there should be some step that should be expected. Okay, usually there's some sort of multilinearization that says that I don't need to consider regular decoupling, I reduce to some multilinear term. Okay, this is expected. The hard part is trying to figure out what these two things are. What is the most efficient way to iterate these things? And often you just have to try enough. Yeah. Yeah, there's no big theorem that says, if I prove these estimates, then I always win. Yeah. Yeah. Okay.
Thank you very much.
Yeah. Yeah, thanks.